Okay, I'm recording this class from now, from this moment, so anyone from this moment on can see this class. Anyone has access to this class, anyone at all, okay? So there are two people at the moment. Again, I'm just going to make sure that we get this thing done correctly. Control V, I'm just going to say that again. If you cannot hear me, refresh the page and the option to listen only when prompted. Okay, that's what you have to do. And what we're going to do now is we're starting recording now, and what I'm going to do is I'm going to do the Examcraft question 1 from this year's mock. We're going to go through that. It's nice and easy, it's nice and straightforward, and we'll continue on with that one for a while, okay? I might do a couple of questions throughout it as I'm going down. There was a nice differentiation question, and there was a nice other couple of things as well. So we'll get started now, just one moment. Just maximize the window there by clicking on the webcam window and maximize that. Okay, now it's kind of, I would really like actually if the other two could hear me. I don't think they can. Okay, just before we start, I'll get this done. Okay, you can actually change the size of the windows as well. What I generally do is I make it about 3/4 of the size of the screen and just leave the chat box open on the right, so that you can kind of keep an idea as to what's going on, and if people are chatting and asking questions, you can just make the webcam window as big as you like, okay? So, right, we're going to start with the question that I want to do with you today, which is, we're going to start with question 1 from this year's mock. So it's the 2020 Examcraft mock, paper 1, question 1. We'll start there, okay? And it says, the first one, it's fairly straightforward. It says solve 2x squared minus 11x plus 15 equals 0. So this one, a very nice start to an exam. Very nice altogether. So now again, if you can do this in your head, it's fantastic. If you can do it in your head, and if you can't, we have other methods to do it, the guide target and all of that. So let's see, we're going to just see that's going to be a 2x and an x, and it's going to be 3 and 5. I'm going to put my minus 3 there and my minus 5 here, and what we get is 2x by minus 3 is minus 6x. Minus 5 by x is minus 5x, and when you add the two of those, you get minus 11x, which is the number in the middle. Okay, so that is equal to 0. Then we put each factor equal to 0. 2x minus 5 is equal to 0. 2x is equal to 5, so x is 5 over 2. X is 5 over 2. The next one then is x minus 3 is 0, so x is equal to 3. Okay, so there are the two answers to that. Very straightforward. Hi, Aideen. Hi, Aideen. How are you? Okay, so that's the first part done. That's part 1A done. Let's do part 1A2. It says then, hence solve the following. Hence solve. And the question is, hence solve 2 times 1 over t squared. To be fair, this is a junior cert question. This is a junior cert honours question. So this shouldn't cause any problem to anyone. Okay, so hence solve this equation instead. I mean, you should have been aiming for a full 20 on this, or a full 10 on this, if that's what was going for it. So let's have a look at this. This is exactly the same as 2x squared minus 11x plus 15 equals 0. If x is 1 over t squared. That's exactly the same thing as that. Okay, that's exactly the same thing as that. So what we're going to say is, we know the answer to this question. We know that means that big X would be 5 over 2, or big X would be 3. That means 1 over t squared would be 5 over 2, or 1 over t squared would be 3. That means 2 over 5 would be t squared. For this one here, you just multiply the 2 up, divide the 5 down, and multiply the t squared across. And exactly the same over here. 1/3 would be t squared. So t here would be plus or minus the square root of 2/5, or plus or minus the square root of 1/3. Plus or minus the square root of 1/3. Okay, so that would be the answer to that question. That would be the answer to that question. All of those make sense. There's 4 solutions to that equation. There's 4 solutions to that. You would lose marks if you didn't put the plus or minus on either of those. Okay? Good. Any questions about that question now, or will I just move on to the next one? Okay. Good. So we'll go on to the next one. So. Okay, the next one is it's a bit more difficult now. It's an induction question, so we'll start on induction. So this is part B, and it says, show by induction that the following is always divisible by 6. So show that n times n plus 1 times 2n plus 1 is always divisible by 6. Is always divisible by 6. Is always divisible by 6. Okay, so this is an induction question. And we're going to go through step 1, step 2, and step 3. But first of all, I'm just going to make it a bit easier for the examiner to understand me. And I'm just going to define a couple of things before I start. Okay, I'm just going to define a couple of things before I start. What I'm going to say is this. I'm going to say that A line B means A divides into B. A divides into B. So we're going to start with that. A divides B. Okay, now we're then going to say if A divides B, this implies that A is equal to B multiplied by M for some M, an element of N. So that's the second thing we're going to say. Okay, if A divides B, then that means that A is B times some number. A divides, oh my God almighty, B is equal to A times M. That means that B is equal to A times M for some M, an element of N. Okay, and the next thing I'm going to say as well is that if A divides B plus C and A divides B, then A divides C. That's the other thing. Okay, if A divides B plus C and A divides B, then A divides C. That's just a fact. Okay, think about it. If you're not sure about that, just have a think about that. That's just a fact. Okay, so knowing that, we're now going to start the question. Okay, we're going to start this question here. Okay, good. So step 1, we have to do these out. So step 1, show it's true if n is equal to 1. Show it's true if n is equal to 1, i.e. show that 6 divides into n times n plus 1 times 2n plus 1, where n is 1. Okay, so 6 divides into 1 times 1 plus 1 times 2 plus 1. 6 divides into, that's 2 times 3, which is 6, and that is true. That is true. Okay, so that's the first part done. Step 2. Step 2. We then assume it's true. Assume true if n is equal to some number k. Okay, i.e. we're going to say 6 divides into k times k plus 1 times 2k plus 1, and we're just going to assume that that's true. This means that k times k plus 1 times 2k plus 1 is equal to 6m for some m, an element of n, for some number. So if we're saying that 6 divides into it, then it is 6 times something. It is 6 times something. Okay. The next step is step 3, and this is the inductive step. Step 3 is the inductive step. This is the money inductive step. And the inductive step is we must now prove true if n is equal to k plus 1. Okay, we're going to prove if it's true in that instance, i.e. prove that 6 divides into, so instead of n, I'm going to say k plus 1 for each of these. So the first one is k plus 1. The second one is n plus 1, which is k plus 1 plus 1, and that's k plus 2. Okay, and the third one then is going to be 2 times k plus 1 plus 1. So instead of n, I'm going to say k plus 1. N is equal to k plus 1. So in other words, 6 divides into k plus 1 times k plus 2, and this one is going to be 2k plus 2 plus 1, which is 2k plus 3. So that's what we have to prove. We have to prove that 6 divides into this object here. We have to prove that that is true now. Okay, so that's what we have to do. That's the setup. Now, if you did this so far, and this was, we'd say, a 15-mark question, you'd probably get about 7 or 8 out of 15 for doing this. So no, that's what this is about worth. The main portion of the marks is for this inductive step, though. Okay, so what we're going to do is we're going to say the following thing. The proof is this. The proof is the following. I'll actually do it on the next board. Okay, we're going to do that in the next board now. So at this stage now, you should have pen and paper out. You should be taking all of this down. You should be seeing, am I getting it right? You should be checking if I'm making any mistakes, and you should be asking any questions if there's any problems. That's what you should be doing. Okay, so let's go on to the next one. So I'm going to assume you're all fine if you're not asking me questions. So we have to prove that 6 divides into k plus 1 times k plus 2 times 2k plus 3. Okay, we have to prove that that is true, and the proof is this. The proof is this. Okay, I'm going to say that we're going to multiply this out first. We're going to multiply this out. This is the only thing we can do here, to be honest, being realistic. There's normally other ways around it, but this one is you literally have to multiply this out. So we're going to say k plus 1 times k plus 2 is k squared plus 3k plus 2. That's that by that. And I'm going to multiply that by 2k plus 3. By 2k plus 3. So we're going to multiply by the 2k first. We get 2k cubed plus 6k squared plus 4k plus 3k squared plus 9k plus 6, which is 2k cubed plus 9k squared plus 13k plus 6. So that is this object up here, and we have to show that 6 divides into that. We have to prove now that 6 divides into that. So what I'm going to do is I'm going to go back to my step 2, and my step 2 said, if you've got that taken down, I'm going to bring my board back in. I'm just going to bring my board back in very slowly. You got that taken down? Step 2 says that this is definitely true. 6m is this object here. Okay, 6m is this object here. So I'm going to write that down and see what that gives me. Okay, we know that 6m is equal to k times k plus 1 times 2k plus 1, which is equal to k squared plus k times 2k plus 1, which is 2k cubed plus k squared plus 2k squared plus k. And this is equal to 2k cubed plus 3k squared plus k. And we know that that is 6m. We know that that is 6m. Okay? And now we're going to look at what we have on the left and see how that is related to what we have on the right. We're going to see what they have in common and what's the difference between them, particularly what's the difference between them. So I'm going to write this as, this yoke here is, we have 2k cubed plus 3k squared plus k. So I'm going to write what I know over here first, and then I'm going to see what else I need to make this line here the same as that line there. And what I need is I need an extra 6k squared, I need an extra 12k, and this extra 6 also. So this is equal to 2k cubed plus 3k squared plus k, excuse me, plus 6 into k squared plus 2k plus 1. And this is equal to, now we've already said and assumed that this part here is 6m. So this is 6 times m plus 6 times k squared plus 2k plus 1. And 6 divides into the first part and the second part. This implies that 6 divides into the whole thing. 6 divides into k plus 1 times k plus 2 times 2k plus 3 as required. Okay, so that's the first part. And I'll let that settle in for a second. We're not finished yet. There's a spiel we have to give. You have to explain now why that means that we have it done, that we're finished. And there's a spiel that you have to say. And the spiel is this. So, our statement is true, or statement is true for n is equal to k plus 1 if it is true for n is equal to k, and it is true for n is equal to 1. Okay, and it is true for n is equal to 1. So, it is true for all n and elements of n. And that is the spiel that you give at the end of every induction question. You have to say that. It's a really, really, really lovely piece of maths induction. Really, 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 really lovely. And I'll explain exactly what that statement means in a second. Okay, I just want to see how many have showed up. Ah, there's 1, 2, 3, 4, 5. Okay, very, very good. Very, very good. Okay. Any questions on that so far? Any questions on that? Now, this statement here, this is a really, really, really cool statement. And the whole idea behind induction is a really, really, really lovely thing. If you go back to this step 2, here, we say assume it's true. And now I know everyone's saying, but what if it's not? What if it's not true? I mean, and that can happen. Sometimes you assume something's true that's not. Okay, and I can show you ones that would be like that. Okay, so but if we assume it is true, and what we say is if it is true for some number k, then we can also show that the same rule applies for k plus 1. If 6 divides into the statement for k, it will also divide into the statement for k plus 1. Okay, so we never say that it divides into k, we just say if it does, it also divides into k plus 1, which is what we're after proving there. Okay, we assume it's true for k, and then we prove that if that's true, it's also true for k plus 1. Okay, so that's what we did in the next step. So we've said this is k plus 1, and this is in terms of k, and we've brought it down here, and you can see now that 6 divides into k plus 1 if it divides into k. And the real beauty is we know it's true for n is equal to 1. We know that's true. So if it's true for 1, let k be equal to 1, then it's also true for 2. Because whenever it's true for k, it's true for k plus 1 as well. So if it's true for 1, it's true for 2. And if it's true for 2, it's true for 3. And if it's true for 3, it's true for 4, and so on and so forth. Okay, so this does actually prove, beyond all doubt, that 6 divides into this always. Always. It's really, 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 really smart. Really, really clever thing to do this. Okay? Really, really clever thing to do. Now, I'm actually, while we're at this stage, because to be honest, I just want to show you what we kind of do here, okay? I'm going to show you now one that doesn't work. I'm going to do one that doesn't work, just to show you how induction works, okay? Just to show you that you have to have all 3 things be true. It has to be, you have to show true for n is equal to 1, assume true for n is equal to k, and then prove true if n is equal to k plus 1. So what I'm going to do is I'm going to make up a lie, I'm going to put it down and then prove it's a lie, even though step 2 and step 3 will be fine. It will be fine for step 2 and step 3. So I'm going to do a different one now that makes, just to show that off. Okay, so let's have a look at this. I'm going to say the following thing. Okay, check by induction if, let me see, we'll come up with one. Okay, check by induction if 1 plus 2 plus 3, we'll do it even better than that. 1 plus 3 plus 5 plus 7 plus all the way down to 2n minus 1. So we're adding odd numbers. All odd numbers have the form 2n plus 1. And I know normally this would be equal to n squared. I know that's true normally, that would be equal to n squared. The sum of the first n odd numbers is n squared. So I'm going to make a lie here. I'm going to make a mistake and say it's equal to n squared plus 2. Okay, I'm going to say that that's equal to n squared plus 2. Okay, and now I'm going to prove that induction is going to tell me that that's a lie, even though step 2 and step 3 will be correct. Okay, so I'm going to ignore step 1 for the moment. I'm just going to ignore that for the moment and go straight to step 2. So step 2, I'm going to assume true if n is equal to k. I'm going to assume that that's true. Okay, i.e. 1 plus 3 plus 5 plus 7 plus all the way down to 2k minus 1 is equal to k squared plus 2. Is equal to k squared plus 2. Okay. Now step 3, prove true. Prove true if n is equal to k plus 1. Okay, i.e. prove that 1 plus 3 plus 5 plus 7 plus all the way down to 2k minus 1 plus some extra term. Plus an extra term. Now the extra term is what happens if I make n k plus 1. So when n was k, it's 2k minus 1, which is the previous step. And now I'm going to put n is k plus 1. And if n is k plus 1, this becomes 2 times k plus 1 minus 1, which is 2k plus 1. So I'm going to add on 2k plus 1. Okay, and the formula says, that this should be equal to whatever n is, you square it. In this case, n is k plus 1. So it should be k plus 1 squared plus 2, which is k squared plus 2k plus 3. Okay, so I'm going to prove that that is true if that is true. Okay, I'm going to prove that. And the proof is this. The proof is, well, if you look at this statement here, the whole first part of this statement, the whole first part, 1 all the way up to 2k minus 1, is exactly equal to step 2. So this whole first part is k squared plus 2. Okay, the whole first part is k squared plus 2. And I'm going to add on 2k plus 1. And you do, in fact, get k squared plus 2k plus 3. That is a fact. So whenever it's true for k, it's also true for k plus 1. So whenever it's true for k, it's also true for k plus 1. But, this is actually true for no number, okay? When n is 1, if n is 1, what we get is that the sum of the first 1 odd numbers, which is 1, this says is equal to 1 squared plus 2, which is 3. So for n is equal to 1, it's not true. It's not true. It's not true at all. Okay, it's not true. So that means that my whole statement is incorrect, even though my inductive step is correct. Okay, the step 1 wasn't correct, so the whole thing falls apart. All 3 things have to be true. Step 1, step 2, and step 3. Okay? Step 1, step 2, and step 3. So that's interesting, I think, that we can get formulas which seem true, but they're not. Okay, you have to get all 3 steps. Okay, it has to make sense. Is that okay? We'll move on to a different question if that's okay. Did you understand what I just did there? Please say yes. Good. Good. Excellent. Good. Okay, so induction really, it's a much underappreciated and undervalued method of proof in maths. It's actually one of the most beautiful things that we do in maths is induction. It's a really nice thing. To show that something is true for every single number out there is extremely difficult. We use induction to do that. Okay, so that's perfect. Let's go on to the next question so that I'm going to see here. So I've done question 1 on the mock from the Examcraft mock. I'm going to skip question 2. It looks very straightforward. There's a cubic then on question 3. There's a cubic on question 3. Real and non-real. In fact, no, the next thing I'm going to do is question 4. So question 4 on the mock. Question 4a, this is on complex numbers. I assume everybody has done complex numbers at this stage if you're in 6th year. Okay, if you've done 6th year, you've probably done complex numbers. And the first question is simplify I to the 57. Simplify I to the power of 57. Okay. Now, when it comes to this one here, it's actually what you need to know is the following thing. I'm going to write it down. Anything to the power of 0 is 1. Anything to the power of 1 is itself. I squared is defined to be minus 1, and I cubed is going to be, well, I cubed is I squared times I. That's what it is. It's I squared times I, which is minus 1 times I, which is minus I. Okay, so that's what we get. Now, I'm also going to say, what is I to the 4? Well, let's have a look at this. I to the 4 is simply I squared times I squared. I squared times I squared. I squared is minus 1 times minus 1 is 1. And we get into this loop. Okay, it's back to the start again. And if we keep multiplying by I, we keep going around in this loop. Every power of I is either 1, I, minus 1, or minus I. Because we just hit 1 again, and we keep going around in that loop then again. Okay, so I to the 0 is equal to I to the 4. It's equal to I to the 4. This is equal to I to the 5. This is equal to I to the 6. And this is equal to I to the 7. So this is equal to I to the 8, I to the 9, I to the 10, and I to the 11. Okay, so that's what we're getting here. We're getting this thing. And we can see the pattern emerging here. That 1 is always the power of I that gives me 1 is 0, 4, 8, 12, 16, and so on. Okay, and we would describe those numbers as multiples of 4. The numbers that give me I, the powers that give me just I, is 1, 5, 9, and 13. And it's kind of tricky to describe these. How do you describe these numbers? How do you describe those numbers? So we'll come back to that in a second. 2, 6, 10, 14, and so on. And I cubed, of course, it's 3, 7, 11, 15, and so on. Okay, so these are the powers of I that give me, and that's the number that you get out. And we would describe this as you get a remainder of 0 when divided by 4. When divided by 4. So all of these numbers here, when you divide them by 4, you get a remainder of 0. All of these numbers here, you get a remainder of 1 when divided by 4. Okay? All of these numbers here, you get a remainder of 2 when divided by 4. And all of these numbers here, you get a remainder of 3 when you divide by 4. Okay? So all powers of I, we can just figure out what that number would be by looking at the remainder when we divide the power by 4. So we're going to look at I to the 57. I to the 57. Well, I know that 4 14s is 56. Okay, 4 14s is 56. In other words, when you divide 57 by 4, you get a remainder of... Sean and Abidorni. When you divide 57 by 4, we get a remainder of... If 4 goes evenly into 56, then the remainder we get for 57 is... The remainder is 1. Okay? The remainder is 1, which means it's the same as all of those. 1, 5, 9, 13. In other words, I to the 57 is I. It's simply the same thing as I. Okay? So that's the first question done. Okay, so you look at the power, the remainder when you divide the power by 4. Okay? So that's the first part done. All powers of I are I, 1 I minus 1 minus I. All powers of I are one of those numbers. Next one. Okay, it says part B. So I've probably got 5 marks for that. The complex number Z is 5 plus 3I. That's it. Find the complex number W. So find W such that Z times W is 2 minus 26I. Okay, this is a very, very, very straightforward question. And there's 2 ways to do this. You can do it the obvious way, or you can do it the long way. I'll do it both ways, just to show you that we can. It doesn't really matter. You don't need to have inspiration beyond anything to get the answer to this question. You can follow the steps very, very, very slowly and get the answer. Okay, so the first one is this. We have to find W. We have to find W. So I'm going to say that what you have to understand here, what they want you to understand, is that the rules of complex numbers are the rules of algebra. Complex numbers, they just kind of tie a bow on the book of algebra. They allow us to solve equations that we could not solve before. Okay, they allow us to get solutions to equations which previously had no solutions. Okay, now that's what they started off as. We found out now that they have much more applications in the real world than that. They're not useless numbers. You know, they have very real applications. We just call them imaginary numbers. Okay, we just call them that. But all the normal rules of algebra apply, so that means that W would be equal to 2 minus 26I divided by Z. This would be the most obvious way to do this question. It's a simple division question then, when it comes to complex numbers, and I mean simple as in that's, it's a simple operation, if you can do it. So that's 2 minus 26I divided by 5 plus 3I. Okay, and when you divide one complex number by another, the rule that we use is you take the bottom number and you get the conjugate of that, which is 5 minus 3I, and you multiply above and below by the conjugate. Okay, you multiply above and below by that. Now, if you look at any complex number, A plus BI, if you look at A plus BI, and you multiply it by its conjugate, A minus BI, you always get the following thing. You always get A squared plus B squared. always. That's the answer. Okay, if you multiply that out, that's what you get. Satisfy yourselves that that is true. Okay, and this is actually an interesting thing as well. This is an interesting thing as well. So we can write it like this: a squared plus b squared is a plus bi times a minus bi. Okay, now what's unusual about that is that previously in the junior cert, you would have been told that there's no way to factor the sum of two squares, that we could only factor the difference of two squares. We know that a squared minus b squared is a plus b times a minus b. Okay, we were told we could factor the difference of two squares. We do that all the time. And we were told that you can't factor the sum of two squares. Now you can if you allow complex numbers into it. Then you can factor the sum of two squares. Okay, but that's neither here nor there. We're going to come back to this. And I'm going to multiply the top out first. So the top is 2 by 5 is 10 minus 6i minus 130i plus 78i squared. So 2 by 5 is 10, that's minus 6i, that's 130i, and this here is 78i squared. Minus by minus is plus. And at the bottom, you can see here that we get a squared plus b squared, which is 5 squared plus 3 squared. Okay, and that is, the bottom becomes 25 and 9 is 34. So the bottom is 34 there. Okay, now the top, we look at this number here, plus 78i squared, and the effect that an I squared has on a number is it changes its sign and then goes away. Okay, it changes the sign of its coefficient and then I squared is dealt with. Okay, so this is the same as minus 78. That's minus 78, that number there. So 10 minus 78 is minus 68. And minus 6 minus 136 is minus 136i. Okay? This is equal to minus 68 over 34 minus 136 over 34i. And these numbers are nice because that's minus 2 minus 4i. Those numbers go in nice and evenly. So W is that number there. W is that number there. Okay, now again, I'm not putting any huge pressure on anyone here to get this question done one way in an exam. I'm going to show you a different way to do this question now. Okay, it's a bit more difficult, it's a bit more weird, but if you can try these out, it just gets you used to dealing with complex numbers and what they're about. Okay, there's certain things that we do with complex numbers and we kind of have to do them a certain way. Okay, so I'm going to show you how to do this a different way now. A different way. Hopefully it'll all work out. Huh? Good. So we're going to say that Z is some number 5 plus 3i, and W is some number A plus BI, some number. Okay, and we're going to figure out what W is, hopefully by doing a little bit of lefty-righty and considering numbers left and right and all of that crack. We'll end up with simultaneous equations, a linear and a non-linear simultaneous equation on this, which we're then going to be able to solve, and I'll make sense of all of the answers, all of the possible outcomes that we get from that. Okay, so let's see what happens. It just says multiply Z by W to get this. So let's see what we get when we do that. Again, this is just like if you were not 1,000,000% sure, but you kind of tried something and hopefully it'll work. Well, it will work. It will work. If you're right, you're right. So we're going to say A plus BI multiplied by 5 plus 3i is 2 minus 26i. So when I multiply this out, what I get is I get 5a plus 3ai plus 5bi, plus 3bi squared is 2 minus 26i. That's what I get when I multiply those out. 3ai, 5bi, 3bi squared. Now again, this I squared changes the coefficient, changes the sign of the coefficient in front of it, and then goes away. So we end up with 5a minus 3b. 5a minus 3b is there. And at the other side then we get plus 3a plus 5bi. is equal to 2 minus 26i. This is even more straightforward. This is just two linears. Okay, this is just two linear equations. And this is my real part plus my imaginary part. This is a real number. There's no i's in that. This is the imaginary part. Both of those have an I, is equal to real plus imaginary times I. And if two complex numbers are equal to each other, then the real parts are equal and the imaginary parts are equal. That's the only way that two complex numbers can be equal. So you get 5a minus 3b is 2, and we get 3a plus 5b is minus 26, apparently. Good. So what I'm going to do now, we have two equations and two unknowns. I'm going to multiply that by 5, multiply that by 3. Okay, and we get 25a minus 15b is 10, and 9a plus 15b is minus 78. Then we add these two equations down, and by doing that we cancel the plus and minus 15b. They cancel out, so we get 34a is minus 68, so a is minus 2. And we sub that back into that one or that one, doesn't matter. So we'll sub it into the first one. 5 times a minus 3 times b is 2. That's minus 10 minus 3b is 2. That means that minus 12 is 3b, so b is minus 4. So my a, b is minus 2 minus 4, and my number w is minus 2 minus 4i. Minus 2 minus 4i. So we get the same answer either way. It doesn't matter. You could do the long division, or you could multiply it out and use simultaneous equations to get the answer. Okay, either of those will work. No bother at all. Okay. We can use this approach also, while I'm here, we can use this approach also to get the square root of complex numbers. We're going to get the square root of complex numbers. So I'm going to show you how to do that now as well with algebra, without going outside the rules of normal algebra, okay? So we're going to try to find now, what is the square root of I? What is the square root of I? And I'm going to do this without Damaris theorem. Okay, I'm going to do this without it. Okay, so I'm going to say that some w is equal to the square root of I. It's some complex number. Okay, and I'm going to call it a plus bi. A plus bi. Good. Now, so what we're going to say is this. This means, so this implies that w squared is I. This implies that w squared is I, which is the same as 0 plus 1i. Okay, and w is a plus bi, and when we square that, what we get is a squared plus 2abi plus b squared I squared, which is a squared minus b squared plus 2abi. A squared minus b squared plus 2abi. Okay, so that's what we have so far. So that's what w squared is. And we're going to put that equal to 0 plus 1i. We're going to put that equal to 0 plus 1i. Okay, and again, just like I did in the previous thing, real plus imaginary times I is equal to real plus imaginary times I. So we get a squared minus b squared is 0. And we get 2ab is equal to 1. The coefficient of I on the right is the same as the coefficient of I on the left. And from here what we get is, from this equation here, we get that b is 1 over 2a. b is 1 over 2a. And now these are actually two non-linear equations. In the previous one, I had two linear simultaneous equations. In this one, it's two non-linear equations. What makes an equation non-linear is if you have something like an xy or an x squared or a y squared or anything like that. That makes them non-linear. This is non-linear because it has the a squared and the b squared, and this is non-linear because it's got ab as a product. Okay, so that is two non-linears. But we solve them the same way. We're going to sub this b in over here. So this is a squared minus 1 over 2a squared is naught. Okay, this means a squared minus 1 over 4a squared is naught. This means that a squared is 1 over 4a squared. Okay, and this means that a to the 4 is 1 over 4. A to the 4 is 1 over 4. Okay. Now, how do we get the answer to that? What are the 4/4 roots of that? Well, what I'm going to do is this. To make this a bit easier. I'm going to say that a to the 4 is a squared squared, and that's a quarter. Okay, a to the 4 is a squared squared. In fact, let's just put it like this. A to the 4 is x squared, where x is a squared. So a to the 4 is x squared, where x is a squared. That means that x squared is a quarter, x squared is 1/4. That means that x is plus or minus a half. Plus or minus a half. Now x is a squared, so that means that a squared is a half, or a squared is minus a half. A squared is a half, or a squared is minus a half. Now, when we look at the first one, this is going to be absolutely fine. It's plus or minus 1 over root 2, which is the same as the square root of 1 over 2. Because that's the square root of 1 over the square root of 2. Okay, so you get the same answer. This is the same thing. Okay, so a is plus or minus 1 over root 2 if we use this one. Now, if I was to use this one here, if I was to use this equation here, I would get a being a complex number. A would be a complex number, which is no good to me because a is a real number. Okay, a is a real number, so I can ignore that. I can ignore that for the moment. Okay, I'll just park it there for a moment. We'll just park it there. Okay, so we know what a is. A is plus or minus 1 over root 2. I'm going to get rid of this now. Okay, and we know that b is 1 over 2a. So b is 1 over 2 times 1 over root 2, or b is 1 over 2 times minus 1 over root 2. So this is now 3-level fractions. They're a bit of a bugger. Okay, they're a bit weird to look at. What I think of is there's no such thing as a 3-level fraction. It doesn't exist. And they're actually very, very weird. 3-level fractions are something you have to be very, 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 very careful about. I mean, 1 divided by 2 divided by 3 is not the same as 1 divided by 2 divided by 3. They are not the same thing. They are not the same thing at all. This is a half divided by 3, and this is 1 divided by 2/3. Okay, so 3-level fractions are something we have to be very, very wary about. What you have to identify in a 3-level fraction is what is the whole object. What is the whole number in that sum? Okay, so for example, in this one, the whole number is 3, so we make it a 4-level fraction. Okay, and this now is a fraction divided by a fraction, which is a half multiplied by the reciprocal, and that's 1/6. Okay, so the first one here, 1 over 2 divided by 3 is 1/6, whereas this yoke here, the whole number is 1. The whole number is 1. So this is 1 over 1 multiplied by 3 over 2, which is 3 over 2. So they're completely different answers. So three-level fractions are something you should be very, very careful with. Okay, identify the whole number in your three-level fraction and make it a fraction. Put it over 1. Okay, so that's a very important thing to mention at this point. So we're dealing with a three-level fraction here. So the whole number there is 1, and the whole number there is 1. Okay, so here we have 1 over 1 multiplied by root 2 over 2, which is root 2 over 2, and that's, we actually write that normally as 1 over root 2. Your calculator will say it's root 2 over 2, you're going to say it's 1 over root 2. Okay, and over here, this is equal to 1 over 1 multiplied by minus root 2 over 2, which is minus 1 over root 2. And they're my b's. So my a is, if a is plus 1 over root 2, if a is plus 1 over root 2, then my b, because my number is a plus bi, if a is 1 over root 2, it's 1 over root 2i. And if it was minus 1 over root 2, you get minus 1 over root 2i. And that's how you get the square root of a complex number without using Damaris theorem. Okay, you solve two nonlinears, but you have to be a bit smart about it. And the very, very final thing I'm going to say on this question is the following. The very, very final thing I'm going to say is this, okay? That when we get this situation over here, we got the a squared is a half and the a squared is minus a half. Okay, and I said we can ignore that. I said we can ignore that because it makes no sense because a is a real number. But what we actually get out of that is that's actually the b squared. You can see that that's actually the b squared over there. Okay, the b squared would be that. So you get plus 1 over root 2i and minus 1 over root 2i out of that. Okay, so you do actually, I could have stopped it at that point. I knew my answer at that point. Okay, I knew my answer then. Is that okay? Right. So we've done nearly an hour. I'll do probably one more question, and then you can ask me questions about everything else. Okay, so let's try and get another question from this to see is there anything interesting that we can learn. Okay, the next question then is a Damaris theorem question. Okay, so I better do that, I suppose. We'll try Damaris theorem. I know you're mad for Damaris. I will say this though, Damaris theorem is one of the really, it's the most profound thing you learn in the Leaving Cert is Damaris theorem. I mean, it's so weird and beautiful in a way. You know, it's a really lovely thing. It's really lovely. I mean, you couldn't imagine that it's true. You couldn't imagine that it's true. The fact that it's true is amazing. And you know what I always say about it is, like, we have that if you have a number z, is equal to r times cos theta plus I sine theta, and then we know that z to the n will be r to the n times cos theta plus I sine theta to the n. And the Damaris theorem says that this second part you can multiply the power into the argument. We call these things the arguments of functions. Okay, so the argument here, r to the n cos n theta plus I sine n theta. It's weird. It's a really weird formula. It wouldn't be true. It's definitely not true if the I isn't there. If the I isn't there, it's definitely not true. Okay? So that is z to the n. That's what it says. You just literally multiply in by your power to get your answer, which is really lovely. Okay, so but the first thing we have to do is write our numbers in polar form. Write our numbers like that. Okay, so we're going to get w here. It says w is the number minus 2 root 3i. And it says write w in polar form. Write w in polar form. In polar form. So we have to write it like this. Let me just get back into the classroom here for a moment. Good. So what you do first of all is you just quickly sketch it out. Just quickly sketch where the number is. Quickly sketch where that is. What quadrant it's in is what we want to know. So you go back 2 and down 2 root 3. It's around there. I mean, there's no need to reinvent the wheel here. Like, you know, that's where it is. Okay. And this is or. The modulus of the complex number is or. The distance that it's away from the origin is or. And this angle here, starting at 3 o'clock and working anti-clockwise until we hit that bar, that is the argument. That is theta. That is theta. So we have to find what or is and what theta is. Okay? And we're just going to say now, I'm going to do this in degrees rather than in radians for the moment. So that's 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay? And what we need to know, there's something very, very special that we need to know about this. Okay? To find theta, we're going to use what's called a reference angle. And the reference angle, what I want you to think of it as, is I want you to think of where's the complex number, and I want you to draw a perpendicular to the nearest x-axis, to the nearest real axis. So that's a perpendicular to the nearest real axis, not the y-axis, not the imaginary axis, it has to be the real axis. Okay, you just draw a line from there to the nearest real axis. Drop a perpendicular. Okay, and this angle that you get in the triangle, this angle here, we call this angle alpha. That angle is alpha. And alpha is always the following thing, the inverse tan of plus imaginary over plus real. That's always what alpha is. Always. Okay? And then you have to figure out what theta is, knowing what alpha is. So in this case, alpha is the small angle that's in here. So to get theta, I'd have to go around 180 and then add the alpha on. So in this case, theta would be 180 plus alpha. Okay? Plus alpha. And we also know that or, which is what else we need the or is the modulus of the complex number, or the distance that it is away from the origin. It's how far away from 0 that number actually is. So we'll do that first. You get the square root of, you square the first part, you square the first part of the number and the second part of the number, add them and square root the answer. Okay? There's never an I goes into this. Never, ever, ever. You never put an I into the modulus. And in fact, you can completely ignore minus signs when it comes to modulus as well. Both of these numbers will be positive when you square them. And you will never put an I in, so you will never get a negative number inside there. So this is the square root of 4 plus 12, which is the square root of 16, which is 4. Okay, so or is 4. Good. And we know that alpha is the inverse tan of plus imaginary. How did you get, go on? The point for or. Right, okay, what I said was this. I said the first thing you do is you look at the number w, okay, and you find out where is that number w. Where is it? Where is it? If this was just a normal x and y grid, if it was a normal x and y grid, okay, you would find that number at the point minus 2 root 3. That's where you would find it. Minus 2 root 3. So where would that point be? Well, you go back 2. So here is minus 2. And then you go down to 2 root 3, which is a little bit further. It's a little bit further down than it's back, but it doesn't really matter. As long as you can sketch this out, as long as you know what quadrant it's in, you're absolutely fine. There's or is, I'm just sketching this. There's no grid here at all. There's no numbers here at all. It's just a sketch so that I can picture in my head where it is. Does that make sense? It's literally just to see where it is. It's just to see where it is. So now, and this is the complex number here. This is W here. It's this point is the number. This line is simply it's the modulus of it. Okay, it's the modulus. It tells me where it is really. Okay, so tan coming back here, we have to get alpha now, and alpha is the inverse tan of plus imaginary. So you change, if it's minus, you make it plus. If it's plus, you leave it plus. So that's 2 root 3 over 2, and that's the inverse tan of root 3, and the inverse tan of root 3 is 60 degrees. Okay, so that's my alpha. My alpha is 60 degrees, but I don't want alpha. My complex number is in theta. But I do know from here that from my picture again, that theta is 180 plus alpha, which is 180 plus 60, and that is 240 degrees. Okay, so this angle here that starts at 3 o'clock on your watch and goes anti-clockwise until it hits that arm, that angle there is 240 degrees. Okay, good. Good. So now my complex number W is or times cos theta plus I sine theta, where or is 4, and theta is 240. Cos 240 plus I times the sine of 240. So that's my number W. That's my number W. Okay? Good. That's it in polar form. I'm going to remove all of this now. Now, you always do these the same way. I mean, it's very, very, very samey. You sketch it out. Where is it? Okay? You do these little things. That's grand. And then you write down alpha is always the inverse tan of imaginary over real, plus imaginary over plus real, and or is always the modulus of z. Okay? And that's it. Okay, that's it. And you have to figure out what theta is then, depending on alpha. But theta will always be one of the following things. Theta will be equal to alpha. Theta will be 180 minus alpha. Theta will be 180 plus alpha. Or theta will be 360 minus alpha. It has to be one of those four. Okay, so once you have alpha, this is the first quadrant, second quadrant, third quadrant, fourth quadrant. Okay, it has to be one of those. Okay, good. So now we have our number in polar form, and now it asks me to find the 4 fourth roots of W. Find the 4 fourth roots of W. Okay, now when it comes to finding roots of complex numbers, when we're looking for roots of complex numbers, there's just one thing that we need to do, and that is we need to change our number. We need to change W to what's called the general polar form. The general polar form. Change W to the general polar form. And it's very, very straightforward to do that. If your number is in degrees, all you do is this. We say Wn, we put a little n under it, is equal to 4 times the cos of 240, and you just add on 360n plus I times the sine of 240 plus 360n. Okay, so that's my Wn. If you're doing this in polar form, then you would be adding on 2n pi in both cases. 2n pi if you were doing it in polar form. Okay, so that is my Wn. Now I'm going to get Wn to the quarter. They're the fourth roots of W. And your fourth roots are, so whatever n is here, it goes with the modulus. So it's 4 to the fourth. And then you multiply your number in by the argument. Okay, so this is the cos of, when you get a quarter down, that's 60 plus 90n plus I times the sine of 60 plus 90n. Okay? And then what you need to do to get the answer is choose any 4 consecutive n's. Choose any 4 consecutive n's. Okay, and the 4 to choose would be obviously 0, 1, 2, and 3. The value that we get for 0, special name for that, that's called the principal root. The principal root is for n is equal to 0. Okay, principal root is for that. So we get, if n is equal to 0, n is equal to 0, we get W0, which is one of the answers, W0 to the quarter. We'll call that Z1. Z1 is, I'll call it Z0 because it's, Z0 because n is 0. So we get 4 to the quarter. Now that's the square root of the square root, which is root 2. Okay, and then you put n is 0 and we get cos 60 plus I sine 60. That's your principal root, cos of 60 plus I times the sine of 60. N is 0, that just goes away. This is root 2 times a half plus root 3 over 2i. Okay, and this is 1 over root, I'll just go the other way I suppose, root 2 over 2 plus root 6 over 2i. And that's my first one, Z0. Z0 is root 2 over 2 plus root 6 over 2 times I. So that's my first one. My second one now is for n is equal to 1. So when you put n is equal to 1, we get, I'm going to call that Z1. So Z1 is, again, that's root 2. And now we're going to put n is 1. So this is 60 plus 90, which is 150. That's the cos of 150 plus I times the sine of 150. Okay, sine of 150 is the same as the sine of 30, which is a half. So that's going to be a half there, I. And the cos of 150 is the same as the cos of 30, but an opposite sign. So that's minus root 3 over 2. And we're going to multiply that by root 2, and we get the following thing. We get that Z1 is minus root 6 over 2 plus root 2 over 2i. That's Z1. And we then continue on. Hopefully you're following this. We're going to get n is equal to 2. N is equal to 2. Now when we do n is equal to 2, the only thing that changes is the argument. That's the only thing that changes. The root 2 stays the same, but now I'm going to be putting n is 2. So 2 90s is 180. 180 plus 60 is 240. Okay, so the cos of 240 plus I times the sine of 240. The cos of 240 is minus a half, and that's minus root 3 over 2i. So we get Z2 is minus root 2 over 2 minus root 6 over 2i. Okay, that is my third solution. And my fourth solution, which I'm going to call Z3, which is when n is equal to 3, up here. That's 270 plus 30 is 330. And here again is 330. And that's going to give me a minus a half there, I'm sure, and a plus root 3 over 2 there, I'm sure. Okay, and what we get there is we get root 6 over 2 minus root 2 over 2i. Good. And they're the fourth roots of that complex number. They're the fourth roots. Powers are easier to find. Whole powers are easier to find because we don't have to go to general polar form. But But if you're looking for roots, you have to do it in general polar form. It has to be done in that format. Okay? Very, very good. Okay, now there's, I suppose, one other thing that I want to mention here is these look a bit weird. None of them are conjugates of each other. They're all different numbers, and in fact, they're all 90 degrees apart. They're all 90 degrees apart. We can sometimes just use the principal root to get all our other solutions. I could have just used my principal root to get that just by drawing a little picture and adding 90 degrees 3 times. Okay, so what we'll do now, lads, if you don't mind, I'll just stop recording for a moment anyway. I'll just stop recording that.